Hello and welcome to this session where I will be explaining about voltage in series and parallel circuits. But before we start, I want you to think about this starter question that's on the screen right now. What is electric current? We've already covered this in previous lessons. You should be able to answer this question. Pause the video now and write down what you think the answer should be, and then press play to find out whether you were right. Okay, so you should have written that current is a flow of charge. And what is the charge that's moving? It is electrons in the circuit. Okay, good. So we're going to go on now to look at how we measure voltage in series circuits and in parallel circuits. And we're going to be explaining how voltmeters are placed in a circuit, and we're going to be looking at the effect of potential difference, which is the same as voltage, on current. Okay, so first thing to remember is that a series circuit has got no branches in it, and we measure the amount of current in a circuit using an ammeter. So if we were in the classroom, we'd be setting up these circuits, but I'm going to have to do this by showing you on the screen now. So here we have a series circuit with two cells in it and two lamps. Okay, and we know it's a series circuit because there are no branches anywhere in the circuit. Now, we could connect an ammeter into the circuit at any one of these four positions. Remember, the symbol for an ammeter is this. So we could connect the ammeter here, and if we did, the table's saying that we would get a current reading of 1.0 amps. If we had an ammeter connected in this exact same circuit in position 2, the reading we would get would be 1.0 amps. Similarly, if it was in position 3, it would be 1.0 amps. And in position 4, it would be the same. That's because the current is the same everywhere in a series circuit. So there is a misconception that current is somehow used up as it goes around the circuit, and that's not true. What we've got is we've got little electrons travelling around like cars on a racetrack. So those electrons are moving around the circuit and they're just going round in a big loop. So if you were standing here, imagine you were a spectator at a race and cars were going round the track. If you were standing in position 1, you might count, let's say you count 100 cars go by in position 1. If you had a friend who was at position 3 and they were counting, they're going to count the same number of cars as you, because the cars are going round the circuit and they're going to go past you and they're going to go past your friend who's at position 3. It doesn't matter where you are on the circuit, you are going to measure, you're going to count the same number of electrons every time. So the current is a measure of how many electrons are going by in a certain time. Okay, so let's think in summary here. A series circuit has got no branches in it. We measure current with an ammeter, and in a series circuit the current is the same at every point. So that means you can put an ammeter anywhere you like in a series circuit. Right, so let's think about potential difference. What do we mean by potential difference? Potential difference is often referred to as the voltage in a circuit, and all that is, it's the push. It's how hard the electrons are being pushed, how much energy they've got to make them go round the circuit. So the potential difference is a measure of energy, and we measure that using a voltmeter. And you notice the terminology, it says the voltage across a bulb. We have to connect a voltmeter in parallel. So look at this circuit here. What we've got is a branch here and here, and we're connecting the wires of the voltmeter to the circuit like that. So we talk about this being a parallel circuit because we've got a branch here. The ammeter, look, it's in series, that's just one loop there, but this is connected in voltage. In parallel. So here we have a simple circuit. Just like before, we've got a power supply, so I've got a battery of 2 cells. So just be careful of that word cell, because that word we use in several different ways in science, don't we? In this context, we mean the energy source that makes the current flow. If I've got 2 cells together, then we refer to that as a battery. So normally the voltage of one cell is 1.5 volts. Okay, so you need to record these voltages onto your worksheet. I've got another cell here and it's identical. That is also 1.5 volts. Now think of the cells as giving the electrical push in the circuit. So just like a locomotive, steam locomotive might push the carriages along the track, the cell pushes the electrons around the circuit. Now if I've got 2 cells, and look, they're both facing the same way, so they're both pushing together, the push of the 2 cells adds together. So if I add together those 2 cells, the total potential difference, the total voltage, the total push in the circuit is 3 volts. So they're pushing the electrons around the circuit, through this lamp, through that lamp. So these 3 volts of push are shared between the 2 lamps. So what we would find is that if these lamps are identical, then that means that we would get a potential difference of 1.5 volts here and also 1.5 volts here. Now in the classroom it doesn't always work out exactly, usually because the 2 lamps are not quite identical, but what you will always find is that these 2 values will add up to 3 volts. So make sure that you record your values onto your results table, and make sure that you record the conclusion that the voltage across the 2 lamps combined is equal to the total voltage from the power supply. This is a parallel circuit this time, so ignore the red wires because they're joining up our voltmeter. Just ignore those for now. You can see we've got a battery here, 2 cells together, which is providing the energy for the circuit, and the current will flow around the circuit till it gets to this point and there's a branch. Some of the current can flow this way and some of the current can flow that way. Okay, so let's think about the potential difference, the amount of push. So I've got 2 cells together here, so the voltage here will be 3 volts. Now what we find is that we've got this lamp connected in parallel across this power supply, so we would find that this would also be, would also be 3 volts. This one we find has got the same voltage because that's still connected across the power supply, so that is 3 volts also. I can't control this pen for some reason, sorry about that. That will be 3 volts also. So when we have components, in this case these two components are lamps, connected in parallel, they will have the same voltage as the supply, 3 volts, 3 volts, 3 volts. So potential difference, or voltage, is the push in the circuit. It measures the amount of energy that is being supplied. So if you add more cells, we get more push, we have more energy, and that increases the voltage. And we talk about a drop in voltage as you go around the circuit. So in series, you add up the voltage drop across the lamps. In parallel, the voltage across each lamp will be the same as the voltage of the supply. So just remembering what we learnt about current and charge, electric current is a flow of charge, and the charged things that are moving in a circuit are electrons. And metals are really good conductors because they've got these things called delocalized electrons, and the point about them is they can move freely in the circuit. So a cell, which is our source of energy, creates a potential difference, so a push, which makes the electrons flow around the circuit. And we had that formula, didn't we? Current equals charge flow times time. In fact, we could, if we write that as a formula, then we can write Q equals I times T. So in fact we could say we shouldn't give up ever with physics, because you should never quit. Bad physics joke there. Okay, so potential difference when we're thinking about charge is the energy divided by the charge. Okay. If we're thinking about resistance, then we have to think that these electrons have to force their way around the circuit, and the little atoms are vibrating, and it makes it quite hard for the electrons to get through, and we call that resistance. And we've got a formula for that, which is V equals I times R. Okay, so the resistance, or put another way, the resistance is V over I. So if you look at this magic triangle, you can see that the resistance is equal to the voltage divided by the current. But I remember it as V equals I times R, because that's nice and easy to remember. Which brings us to Ohm's law. Now, there was a scientist called George Ohm that discovered that the voltage and the current are related. They're connected. And what he found was that the current is proportional to the voltage. So what does proportional mean? Proportional means if I double the voltage, I will double the current. Or if I halve the voltage, I'll get half the current. The two things are proportional. And that will work all the time as long as the temperature doesn't change. And that's now known as Ohm's law. And that's actually named after George Ohm. Okay, notice the spelling of his name. It was a German name, so it's not quite spelled the same as we spell it here. So what four things affect the resistance of a material are temperature, length, cross-sectional area, and the type of material. So with temperature, if you increase temperature of the wire, all the little atoms vibrate more, and that increases the resistance. If they've got a longer wire, it's harder for the electrons to get through, so that increases the resistance. Cross-sectional area, that's the fatness of the wire. A fatter wire makes it easier for the electrons to get through, and a skinnier wire with a small cross-sectional area has a higher resistance because it's harder for the electrons to get through. And then the fourth thing is what the wire is made of. So some materials are just better conductors than others. So metals like copper have got these free electrons which are able to move through the wire quite easily. So copper's a great conductor. Gold is an even better conductor. If we could afford it, we'd make all our wires out of gold. Other materials are not so good conductors, so they have a higher resistance because these electrons find it a bit harder to get through. So when something obeys Ohm's law, we get a graph that looks like this. As I increase the potential difference, I also increase the current that flows. The two things are proportional. I can tell it's a proportionality. I can tell it's proportional because it's a straight line that goes through the origin. And if I reverse, if I apply a potential difference which is opposite, I get a current flow in the opposite direction. So this is something that obeys Ohm's law. And if you remember, I said that Ohm's law works as long as the temperature doesn't change. If the temperature changes, then we get a graph that looks like this. We get a curve. So I can tell it's not obeying Ohm's law because it's not straight. And this sort of S shape is because as the temperature goes up, the resistance goes up as well. So you can see that at high potential differences, the current isn't going up as much as it ought to. So if the line was straight, it would be going up here, wouldn't it? But I'm not getting as much current, and that's because the wire's getting hot. Right. So what kind of resistors have we got? We've got thermistors. So therm, as the name suggests, it's to do with heat. So a resistor whose resistance changes with temperature. So they're used in a thermostat, for example. And then we've got a variable resistor, which we would be using in class if we were able to do some work on this. And you can see the little slider there. You can slide it up and down. That changes the resistance. That's called a rheostat, this thing here. And this is what you'd find inside a hi-fi or a radio or whatever. When you turn the dial, that changes the setting of the resistor. And this is the symbol that we use for a variable resistor. That arrow represents turning a dial or sliding a slider on the rheostat. And then one more type of resistor is a light dependent resistor. So that's a resistor whose resistance changes as the light changes. So these arrows here, look, they represent light falling onto a resistor. So that shape is a resistor, isn't it? And then we've got these arrows, so that's light shining on a resistor. So that's the symbol for an LDR, a light dependent resistor. So with this one, this used in things like night lights and stuff like that, when lights come on automatically at night, because they can sense by the resistance, we know how bright the light is. So there's one more component I'll quickly tell you about, which is not really a resistor, but you will look at when we're doing later on about Ohm's law, is a thing called a diode. And what a diode is like a one-way valve for electricity. So look at the symbol for a diode. It's like an arrow. It only lets electricity flow in one direction. When the electricity tries to flow in the other direction, it comes across a barrier and it can't go. So when you plot a graph of potential difference against current here, what you find is one way round, it doesn't matter what the potential difference is, the current is always zero. But if you do it the right way round, a small potential difference, a small push, no current flows. You get to a certain amount of push, a certain voltage, potential difference, and the current starts to increase, and it's a straight line. So it's a bit like pushing on a door. Okay, if you don't push hard enough, the door won't open. You push hard, a bit harder, a bit harder, a bit harder. Now the door's opening, and the harder you push, the more the door opens. But if you're pushing on the wrong side of the door, when you should be pulling, it doesn't matter how hard you push, the door will never open. Okay, so that's how a diode works. So we're comparing here how we have components in series and parallel. So if we've got a series circuit, then the current is the same through everything. In a parallel circuit, the current through each branch adds up to the current from the cells. The potential difference, though, is shared in series circuits, but is the same if they're in parallel. And resistance, well, resistors in series, you just add them up. And resistors in parallel, well, that's complicated. For GCSE, you just need to know that the total resistance is less than if you had them all in a line, and it's less than the resistance of the smallest individual resistor. Okay, so there's quite a lot of content I've just covered there. What I'd like you to do is I'd like you to answer these questions on your worksheet. What you may need to do is wind the video back and go through different bits and find the information, pause the video, write it down, and then move forward. So just gradually work your way through to find that information out. Good luck with all of that.